All right, good morning. So this is the last lesson for work and power and energy and mechanical advantage, efficiency, specific heat capacity, and all that stuff. So this is the second kind of thermal energy lesson. So last day we learned what kind of the change in energy is. It's just mass of whatever it is times the specific heat capacity of whatever it is times the change in temperature from one state to another. So generally in these equations it was kind of like this question here. If 12 kilograms of water cools from 100 degrees, which is boiling, to 20 degrees, how much heat energy was released to the environment? It's like you boil a pot and then you just leave it and it cools down to room temperature. So let's find out what the change in energy is. It's mass times C times delta T. Our mass is 12 kilograms, our C is 4,200, and our change in temperature is always final temperature minus initial temperature. So in this case it's 20 minus 100. And then we times all these values through, so 12 times 4,200 times minus 80, we get negative 4,032,000 joules of energy. The minus kind of just means the water lost that energy. Alright, so that's something that we saw last day, those types of questions. So we should know how to do that already. Now the concept today is just bringing it up a notch, still use this equation, but using it kind of twice. So there's this thing called a calorimeter. There we go. Which is this here, which is pretty much a box filled with water, and then you put some other material in that water there. The thing about these calorimeters is they're so heavily insulated because they're trying to mimic that the water is not losing any energy. Not like this pot of boiling water that lost all this to the environment. The goal of calorimeters are to lose 0 joules of energy to the environment. Okay, so the only switch of temperature that's happening is between whatever you put in there and the water itself. Okay, so they have a thermometer because you have to read how the temperature changes. But this is really how they investigate how to find a specific heat capacity, because if you can't control how much energy is lost, it's hard to measure what that C value is going to be. Okay, so it's saying usually it is filled with some mass of water at some temperature, and then you stick something else in it, say like a cube of lead, and you then analyze what happens to the temperature. So an example here is we have this question. 1 kilogram of water is at 20 degrees Celsius and it has its specific heat capacity of 4,200. If they don't give you that, we always have our table from last day in our last notes. So they placed a substance, they don't tell us what the substance is, at 55 degrees and it weighs 1 kilogram, or it has a mass of 1 kilogram. And they place it in the water and then they close the lid of the calorimeter so that no energy is escaping and it's just switching. So since this substance is 55 degrees, is hotter than the water, you know that it's going to be losing energy and the water is going to be gaining energy because it always goes from hot to cold. Okay, so in the end the water is going to end up being hotter than 20 degrees and you know the substance is going to be less than 55 degrees. But how much? This is where we get our equation in. We're going to use the same equation. It's the change in energy, I'm going to say, of 1 plus the change in energy, I'm going to say, of 2 is going to equal 0. That's the equation that you're going to use for all these questions. So the change in energy of 1, let's say 1 is the water, and let's say 2 is the substance, whatever it is. So you're saying the amount of energy that changes from the water, that increases from the water, is going to be the same amount of energy that gets lost from the substance. So those two changes are going to be the same, but one's going to be negative to make it so that overall 0 energy is lost in the system because none is getting lost to the surroundings. So in this case, I was going to say something but I've forgotten. I can't remember, but we're going to do a little bit of algebra, and we're going to minus this one onto the other side. So the change in energy of the water is going to be equal to the negative change in energy of the substance there. So we just subtract this term onto the other side, and we get this equation here. Alright, so now we use our equation mc delta T for change in E. So we're going to go the mass of water times the specific heat capacity of water times the change in temperature of water is equal to the negative mass of the substance, specific heat capacity of the substance, and the change in temperature of the substance. Alright, so now we fill in the values, anything that we can. We know there's 1 kilogram of water. Specific heat capacity of water is the highest, 4200. The change in temperature of the water, 20 degrees. And it says after a while both the water and the substance will reach an exact temperature of 25 degrees Celsius, and it's saying this is called equilibrium. So when they both eventually reach the same value and then stop there, that's called the equilibrium spot. So overall our equilibrium spot, that's where this equation applies. So this is at equilibrium that we're talking about. Okay, when the temperatures have reached the same. Okay, so it's not right when you put it in, it's after you've waited a while. The change in temperature is from temperature final 25 and 20. So it's going to be 25 minus 20. The final temperature minus the initial temperature is equal to negative. The mass is 1. Specific heat capacity, we don't know of the substance. And then we went final temperature at 25, initial temperature of 55. So 25 minus 55. And we have to do a little bit of algebra. So 1 times 4200 is 4200 times 5. Should give us 21,000. And then we have 25 minus 55 is negative 30 times negative 1 is 30 times C2. And now we just have to solve for C2, so let's divide by 30 to both sides and we'll end up getting a C2 of 700. Alright, don't stop there, we got to do the unit. So our C value is specific heat capacity, and if you remember from last day, it's the amount of joules per kilogram per degree Celsius of the substance, of this substance, whatever it is. Okay, so that's how much energy you need to heat up 1 kilogram by 1 degree Celsius. Alright, the last type of example you can get in these questions is this one here, and you have to do a bit more algebra in these types. So again, we'll say at equilibrium, we'll know that the change in energy of the water is going to be equal, I'm going to skip a step, the change in energy, but the negative change in energy of, this time lead, they're saying. So here, I'll go the mass of water times the specific heat capacity of water times the change in temperature of water is equal to the negative mass of lead, specific heat capacity of lead, and change in temperature of lead. Alright, so now the mass of the water in this example is 1. We know 4200 for the C value, and then our temperature value, they say it starts at 20, but they don't know what it's going to end at. So we're going to go TF, our final temperature, minus this 20 degrees. Okay, it's really TF minus TI is equal to the change in temperature. And then we have this negative, and it's again 1 kilogram. Specific heat capacity of lead, you'd have to look at your sheet from last day, and we have a table that tells us what it is. So this is going to be 130. And then the change in temperature is, we don't know what the final temperature is going to be, but we can go TF minus, and it starts off at 1200 degrees. Crazy hot. Okay. And then we have 1 times 4200 is 4200 TF. And then 4200 times negative 20, we're going to distribute that in. So negative 20 will give us negative 84,000. And now we have negative 130. And we're going to distribute that inside, times TF is going to give us TF. And negative 130 times negative 1200 gives us 156,000. So now I have it with no brackets, so let's get all the numbers to the right side and all the variable with their coefficient on the left. Okay, so I'm going to add this 130 over there, and I'm going to add this 84,000 over there. Okay, so 4,200 TF plus 130 TF is 4,350 TF. And if I added this 84,000 over to the other side, it would be 156,000 plus 84,000, and this would give me 240,000. Okay, last step, we're going to divide by 4,350 onto both sides, and my TF is going to be 55.43 degrees Celsius. What does this mean? It means that when you place that really hot 1200 degrees hot lead into that water that's only 20 degrees, all that energy from that hot lead will go into the water, and it'll raise the water to 55.4 degrees Celsius, and the lead will actually decrease from the 1200 down to 55.43. And since no energy is lost to the environment in this calorimeter, they're both going to stay at 55.43 degrees and not move from there. And that is the lesson, the last lesson for energy. Thank you.